Hello there, darling people. Today we are going to look at the Newton's second law variation for rotation. We know that in Newton's second law, the net force is equal to the mass times the acceleration. And in the rotation version, if we have more than one torque, then the sum of the torques is equal to the moment of inertia times the angular acceleration. So let's derive how we get there. We'll start with our standard, wonderful, and traditional. Net force is equal to mass times acceleration. And we know that whenever we do any of our rotational variables, we essentially multiply everything by the radius, like the tangential acceleration is equal to the radius times the angular acceleration. The displacement is equal to the angular displacement times the radius. So if we multiply both sides by the radius, we get our net force times the radius is equal to mass times acceleration times the radius. The next thing I want to do is I want to connect our current A, which is really a translational acceleration, to our angular acceleration. So that's alpha times the radius. If I then replace this alpha, that leaves me with net force times radius is equal to mass times alpha times radius again. From here, I'm going to rearrange a little bit to give my F net times the radius is equal to mr squared alpha, because now we can recognize some of our rotational variables. Net force times the radius is going to be my torque, and then mr squared is my moment of inertia times my angular acceleration. So this is my overall equation. In our example problem, we have a baseball player loosening up his arm before a game tosses a 0.15 kilogram baseball using only the rotation of his forearm to accelerate the ball. The forearm has a mass of 1.5 kilograms and the length from the elbow to the ball's center is 0.35 meters. The ball starts at rest and is released with a speed of 30 meters per second in 0.3 seconds. Let's make a list of the variables that we have. First, we have the mass of the ball is 0.15 kilograms. Then we know the mass of the arm is 1.5 kilograms. The length of the elbow, or the length of the arm, is 0.35 meters. The ball starts at rest, so we know V initial is 0 meters per second, and V final goes up to 30 meters per second, and then finally our time is 0.3 seconds. We want to find the constant angular acceleration of the arm and ball. To do that, we know that we're going to need to calculate the tangential acceleration, because that's equal to the angular acceleration times the radius. There are a couple of different ways to do this, but I'm going to do it in two parts. The first part that I'm going to do is going to be to find the acceleration. To do that, I am going to use V final equals V initial plus AT. My m in this equation is going to be to solve for acceleration. So acceleration equals velocity final minus velocity initial divided by the time. And then my substitution will give me that my tangential acceleration is 30 meters per second minus 0 over 0.3 seconds, which gives me a tangential acceleration of 100 meters per second. From here, I can find my angular acceleration using my acceleration tangential is equal to angular acceleration times radius. And then I can rearrange to solve for angular acceleration, which will be tangential acceleration divided by radius. And then I can plug in my values, where I use 100 meters per second squared divided by the radius, which is 0.35 meters. For my angular acceleration, the final value gives me 285.7 radians per second. As we move to the next part of the question, I've brought down all of the variables that we know. It says calculate the moment of inertia of the system consisting of the forearm and ball. One of the things we want to think about here is, what does this system actually look like? So this is a very, very simplified version. This would be my elbow of our pitcher, so that's going to be my axis of rotation. We have the forearm here, which has a length of 0.35 meters. And then we have the baseball, sort of a baseball there, okay, on the end. So this is kind of like a mass hanging down from the end of a thin rod. So that's the first thing that I want to point out to you. This forearm is acting as a thin rod, and then this portion is acting as a sphere, or really a mass on the end of the thin rod. To get our moment of inertia, we know that our general moment of inertia equation is equal to the sum of the masses of the objects times their radius squared. As we try to identify the m version of our equation, we want to be aware of the fact that we have our moment of inertia is coming from the moment of inertia of a thin rod plus the moment of inertia of the ball itself. Let's take a look at the moment of inertia equations for the different solid objects to decide which one we need to use for the thin rod. In this example, we have a thin rod, so that's either this one or this one, but we want it to be about the axis through the end perpendicular to the length, because this is where our elbow would be. So based on that, we need to be using the equation moment of inertia is equal to 1/3 mass times length squared. Now that we've reviewed and found our thin rod equation, we know that the moment of inertia is going to be equal to 1/3 times the mass times the length squared, plus the moment of inertia for the ball, which will be the mass of the ball, times the radius of the ball from the axis of rotation squared. Now we can plug all the components in and get our answer. So we have 1/3 times the mass of the arm, 1.5 kilograms, times the length of the arm squared, 0.35 squared, plus the mass of the ball, which was 0.15 kilograms, times the radius of the ball from the axis of rotation, which was again 0.35 meters squared. When I complete the calculation, I end up with 0.0796 kilogram meters squared. The final part of this question is to find the torque that's exerted on the system that results in the angular acceleration. Our equation for our EMS is torque is equal to moment of inertia times the angular acceleration. Then this equation is essentially the same because we already know the other two components. And then our torque is equal to 0.0796 that we calculated in part B times our angular acceleration of 285.7 radians per second that we calculated in part A. And we end up with 22.7 Newton meters.